Fusion EP Talks tonight on machine learning, an introduction by Robin Summers, who's currently a senior of the Fusion EP program, who did his bachelor's degree in Gent University and who is now doing his thesis also in Gent under Professor Geert Bertoulai. That's probably wrong pronunciation, but you'll correct me. So the floor is yours.
Okay, thank you very much. So, as you can see here, indeed, I'll tonight give you a short introduction to machine learning and also discuss some application for fusion research. So, my name is Robin Summers and my promoter is Geert Verdoolage. Very nice try by Alexis. So, to start, yes, a short motivation motivation of why we are giving this talk. Why is this related to fusion? Why is this in the Fusion EP talks? First of all, machine learning is something very broad. You can see this picture right here, right? A lot of different applications, different domains. I'll get into them later in the presentation. But well, a lot of different domains, and as you can see, one of them I added myself to the picture is fusion. Okay, this is an image of a jet, a mast discharge actually, where you can see a clear ELM, filaments of an ELM basically, and ELMs and disruptions are one of the things we can study with machine learning. So hence why I thought it's useful that I give this introduction to machine learning, also because I think not everyone is familiar with this. I started learning about machine learning start of this academic year. So I hope all of you at least get to know a little what this is about. The outline of this presentation. So if you didn't know yet, we're going to talk about machine learning. In the first part, the second part, and also the third part will be about machine learning. Let's start with machine learning. What is machine learning? We'll first have a look at one definition given by Arthur Samuel, regarded by many as one of the first in the scientific field of machine learning. And he gives a short definition of machine learning is a field of study that gives computers the ability to learn without being explicitly programmed. This is already something meaningful, right? We can work with this. But when one wants to find out the definition of something, what we always do is, of course, go to the ultimate source of information, and this is Wikipedia, right? And so the definition of Wikipedia of machine learning is a subfield of computer science and artificial intelligence that deals with the construction and study of systems that can learn from data rather than follow only explicitly programmed instructions. So this is already a bit more broad, right? We see here also the term artificial intelligence appearing. This will also come back in the next slide. So as a little example of machine learning or AI, you can see here the robot Sonny from iRobot. For those of you who know the movie, I can only recommend it. Already from 2004, so quite old. And this is also something that should be noted here, right? Arthur Samuel said this in 1959. And you can wonder, this is now 60 years ago. So why are we only recently hearing about this huge development in machine learning? And why is this only recently coming to the foreplay? And this is, of course, because now we have the computer power, we have the CPUs, the GPUs, following Moore's law to calculate these heavy neural networks, CNNs, RNNs, and stuff like this. So that's why we had to wait for the computer power to get to the level that we can now use machine learning to its fullest. So this is another infographic about where you can situate machine learning. So we have the term artificial intelligence. This is the outermost sphere. And so, well, as it's written here, study of devices that perceive the environment and define a course of action that will maximize the chance of achieving a given goal. This is still quite broad, and also different things apart from machine learning fall into this category. Basically, anything that mimics the behavior that we as humans show can be cataloged as artificial intelligence. But a big part of this artificial intelligence is machine learning, right? The subject of this talk. So, as we said already, a subset of artificial intelligence, and machines learn how to complete a certain task without being explicitly programmed to do so. Remark also, this explicitly programmed to do so was also apparent in the definition of Wikipedia. So what this basically says is we didn't give the computer the information, in this situation you had to do this. Often this happens when we code, when we program, we say, if this situation happens, do this. If this happens, do this. But now we leave the do this open, and we leave the chance for the device, for the computer, to decide what will be his reaction to this certain situation happening. This is basically machine learning. And then a subset of machine learning is deep learning, which is a very, very popular term nowadays. And so, well, there they use deep neural networks. I won't be going into detail because it's very complicated. But basically, well, this is very hot, and all of the high tech and high class advanced AIs, they are done with deep learning. When do we use machine learning? As I said, there is a broad range of different applications, but we can distinguish 3 different purposes. When something is too complex for us to handle, say something like speech recognition or even face recognition, we can all recognize someone's voice when we hear them. You can recognize the voice of your mother or your brother when you hear them. However, it's very difficult to quantify this, to say exactly, this is why we recognize it. This is very difficult to put into a theoretical model. And this is why, or when, machine learning comes handy into play. Another one is tasks are constantly changing, like fraud detection. Thieves and criminals will always try to get around certain security measurements. So in order to be ahead of this, we can have a machine that adapts real time. And this is also the case for data that keep changing. Something like the stock price is updated, I don't know, each millisecond or something like this. And so this would be very difficult for humans to keep track of, which is what was done before. But, well, now we can just let algorithms do this for us, and this makes our life much easier. Okay, so I hope all of you get a grasp of what machine learning is. Maybe everyone still has a bit of a different idea in his head. And now we can dive into a bit of the details of what machine learning can do. So we can distinguish between 3 types of machine learning: supervised, unsupervised, and reinforcement learning. This is very important, the distinguishment. This will also come back during the presentation. Supervised, meaning task-driven. So we want to know what is the next value based on previous values. Unsupervised is data-driven. This means we get the data, and then we want the data to speak, as we say. We want the data to give us information. We will extract information purely from the data. This unsupervised, and a reinforcement learning is actually quite a different branch where robots or agents learn from mistakes. So they get rewarded for good actions, they get punished for bad actions. We'll be mainly talking about supervised and unsupervised, although I'll show an example of reinforcement learning as well. Here you can see again another branch description of different machine learning types. So you can see here again supervised, unsupervised, and reinforcement learning, but you can split even further. For example, classification for discrete supervised learning, or regression for continuous supervised learning. And then you can see a couple of different applications. Then clustering, also for discrete unsupervised learning, or dimensionality reduction for continuous unsupervised learning. And then reinforcement learning, as I said, a bit different than the other 2. So let's start with supervised learning. This is a very nice sketch I found. It maybe looks a bit weird, but it's a very good representation of how a supervised algorithm goes to work. Okay, I'll also give a visualization of this sketch in the next slides. So what we do is we collect data. Let's say a lot of images from cats and dogs. Then we extract features. If you haven't heard yet what features are, features can be anything. They can be, well, brightness of the pixels, a certain area of pixels compared to other areas, but they can also be like length of the ears of the cats and dogs, which are already more advanced than just brightness of the pixels and stuff like that. So basically, we characterize each image by the features it has. Then, and this is crucial, this is why we call it supervised learning, we have the labels of the images. So we know for each image, we know if it's a dog or a cat. It's very important. So we have data where we can train on. We know these are cats and these are dogs, and this is the result we want to have. And then the magic happens, right? Then we apply the machine learning algorithm. There's a couple of fancy terms here, like support vector machine, decision tree. We can also put here neural networks, regression, all types, quadratic, linear, and so on. Then we get the model. So after training for a while, a couple of hours, couple of days, depending on the length of your algorithm, we get the model. And this model, if it sees a new image, let's say from a cat or a dog, then our computer or our model will be able to say, this is a cat or this is a dog. As I said, I have a visualization here of this process. So first, we gather all of the samples. These are the gray dots here. So we gather, I don't know how many, around 15 images of both cats and dogs. Then we extract the features. For now, because we want to make it visible, we'll use only 2 features, so we can plot it in 2D, but basically you can extract as many features as you want. Often more than 100 or thousands of features are extracted. So now we look at the length of the tail of the animal and of the diameter of the ears. So this can be extracted from the image, right? And then, well, for each image we can extract this and we can plot the dot inside the graph. So this is the feature extraction, a very important part of the process. Then, as I said, we have the labels. So we know which image is a cat and which image is a dog. So let's say we color the cats green and we color the dogs blue. So let's do this. So we know which one are the cats, which one are the dogs. Okay, and in the end we end up with a division. These are the cats and these are the dogs. You can see there's a clear separation. In reality, of course, this will be much more mixed, but this is an ideal scenario. So we have the labels, we have the features, and then we will train the model. And so what we can see is this very clear by eye. We want to have a separation, and the separation in this case is just a straight line, right? This is just done by linear regression. This can be simply done because it's a very easy example. As I said, they are nicely separated. So then we have the model. And what is the model? The model is just the equation of this line. This is what our model has become, right? We have done all of the calculations, and in the end, we end up with one equation of the line. And by knowing this equation, we can predict anything, right? So if we have a new image, and we measure the diameter of the ears, the length of the tail, well, the computer does it for us. This is this image. Well, then our algorithm can say, well, this is a cat, so this is a green one. And this is exactly what we want to do. We want to predict whether it's a cat or a dog. And by this, we can do classification. We can gather thousands and thousands of images, and our model can say, this is a cat, this is a dog, and so on and so on. So this is concerning supervised learning, where we have the labels. I put stress on it again, because here you can see the process is basically the same, except there is no step where we have the labels. So we just have 10,000 images, but we don't have the labels, which is almost always the case in the real world, right? You gather data, but you don't have time or you don't have it implemented to label the data. So if you want to label the data, you really need someone that puts this is a cat or this is a dog. You need a human looking at the images and saying this is a cat, this is a dog. So this is very time consuming. So that's why often we don't have labels. So again, we just start by samples, gray dots. We extract the same features, but now we don't have the labels. So we don't know which one is a cat or a dog. But the nice thing is there are algorithms out there that can do unsupervised learning, like clustering, and they can try to find their own separations. So what a clustering model here will do is it will find two different clusters. So one cluster here and one cluster there. Of course, it doesn't know which one is a cat or which one is a dog, but it knows that it has found two different clusters. Again, because it's a very nice and ideal scenario. So this is very easy, but so this is very powerful, as you can see. We don't need any labels. We can just have the algorithm learn by itself what are different clusters. A disadvantage is that sometimes or often you have to say how many clusters you expect. So if you say you expect 2 clusters, as we did now, then the algorithm will probably find these ones. Oh. And so the stars are the centroids, as we call them, the centers of the clusters. So I hope everyone got the big difference between supervised and unsupervised learning, the labels, basically. And then, as I said, there's a third one, reinforcement learning, very different. You can think about this as this mouse inside a labyrinth. So what the mouse will do when it tries to find its way out, it will try a lot of different routes, but the one where it ends up bouncing its head against the wall, well, it won't go there again because it knows it bounced its head against the wall, so it won't, well, he won't do this again, at least if it's a smart mouse, right? So what we do is we let agents decide whether they do an action or not, and if it's a good action, so if it passes, for example, a gap, then we reward them with a piece of cake or with a piece of cheese. But if it's a bad action, we punish them. And well, yeah, it's very complicated, but this is an easy way of putting it. So we reward agents for doing good actions, and we punish them for doing bad actions. And then in the end, if you leave them long enough time, like with the mouse, they will figure out, excuse me, the way of getting out of the labyrinth. And this is what reinforcement learning can also do. Okay, then the last theoretical part, model components. So what does a machine learning model consist of? Basically, a parametric mathematical model. So this, for example, the equation of the line, as I told you. So y is 3 times x plus 5, but again, a very simple expression. These can be very complicated. A cost function to optimize. Let's say you want to optimize the least squares error, as you have probably all done when you do regression analysis. You have to put some kind of error that you want to optimize. And then thirdly, the learning algorithm you want to use. You can choose between a wide variety of algorithms. There's a lot out there. And so basically it's up to you to decide which one is perfectly suited for your task. And this is not a trivial assignment. This usually demands a lot of experience to know which algorithm and which cost function is suited for which problem. And then, as maybe some of you noted, there's one big thing missing here, and this is data. Data. So we need a lot of data, right? This is crucial for machine learning. You cannot do machine learning if you only have 5 images, because then the model will not be able to learn enough so it can classify other images in the future. So whatever happens, more data is always welcome. That's why Facebook wants you to tag people on their website, because then they have more labeled images of people. That's why Google wants you to post reviews, wants you to put pictures, because they have more data. It's always about gathering more data. So this is something you have to keep in your mind, right? Okay, now let's look for some applications, because maybe up till now it was a bit, well, it was not so theoretical, but just on paper. let's now look for some applications. Classification, for example, is something which happens in all of your email accounts. So when an email comes in, a model has to decide whether this is spam or this is not spam. For some email accounts, this will be a very effective model. For some, it won't be so effective. But anyway, this is a kind of classification that has to happen, a binary classification. It's either spam or not spam. And it will decide based on a lot of features, as I said. One feature is maybe the email address. One feature is the use of capitals inside the text, and so on and so on. A lot of features. A second one is a very famous one from the ELMS database, where a model, an algorithm, has to recognize which number from 0 to 9 is written here. So these are handwritten digits. And so the algorithm has to say, this is a 1, this is a 2, this is a 3. This very nice data set, which is freely available if you want to try to get to learn some machine learning. So this is classification, this is discrete. And now we can go to regression. One of these is, for example, to estimate the stock price. Of course, you can never really estimate the stock price because you never know what's going to happen, but you can try your best with machine learning, try to see what will be the next stock price, right? This is also something which can be done for pricing in general. If people want to see what is a competitive price, let's say a store wants to know how much should we charge for this t-shirt to be both competitive, but also get us enough money. Well, then it can look at other data that is available and it can say, okay, this is our price. If there's a discount price, it will be this price. So this is regression. Then we go to unsupervised learning, dimensionality reduction. This is a bit complicated, so I won't go much into detail. But this is used, for example, if you have 2D data, which have to be reduced to 1D data. This can also happen for way larger multidimensional spaces. So you can have 300 dimensional spaces reduced into 2-dimensional spaces. Very useful for visualization because our mind can only progress 3 dimensions at the same time. So that's why this is useful. If you were a bit smarter and we could look into more dimensions, we wouldn't need this kind of dimensionality reduction. And then we have clustering, something which all of you are familiar with because this is what all of the big companies concerning recommendations use. So Spotify that has to play the next song, Netflix that says, you liked this series. Maybe you would also like this series. These are all clustering algorithms. And these companies also very often write out competitions and they say, help us to improve our algorithms. And then they give prize rewards. And then finally, we have reinforcement learning. So I'll show you this nice GIF about AlphaGo Zero, which is an algorithm developed by Google DeepMind that learns to play Go. Go is a very complicated game for those of you who know it. And there's like, I don't know how many combinations, but a zillion different combinations. And basically, there's no mathematical model to win the game. So one has to win by experience. And so you see, after 21 days of training, the algorithm, AlphaGo Zero became the best Go player in the world. So it beats all of the humans that had 40 years of experience playing Go. So, well, I don't know about you, but I find this very impressive. And this is another proof that reinforcement learning and machine learning in general can do a lot of things. And maybe one of the reasons why people are scared about AI, because they are smart, but we still have them under control. So there's not really need to be scared, but they are powerful. We have to keep this in mind, right? Now to the third and final part about this presentation, because this is where fusion will get involved, hence the 3 exclamation marks, of course. So fusion and data, just to make a number. So every pulse in Gent, let's say it lasts around 30 seconds, this will produce around 50 gigabytes of data. Nowadays, this is still actually quite reasonable, but for a human to analyze, this is still a lot. If you do a couple of pulses each day, you will need a lot of master students to analyze all of this data. So we want to automate this, of course. We want to use machine learning models and algorithms for us to extract the data, not only because maybe we don't want to spend time, but also because they might be smarter than us. They might be able to extract more data or more lessons from the data than we are able to. And this is where my thesis subject comes into play. So I will be analyzing ELMS basically. This is a visualization of a discharge shot from Compass Tokamak in Prague. You can see the H mode window indicated, and all of these big spikes are ELMS. So what we will do, what I will do together with my promoter, so Geert Verdolager, is analyze a lot of ELMS. So this is a jet discharge. So first an algorithm had to be created to detect ELMS. This is still under construction, but being created now. So this is what you can see here. Well, these are more than, I don't know, 60 or 70 ELMS in one discharge. So this would be very hard to identify by hand. And once this is done, we can analyze the characteristics. So these are plots that some of my colleague students will recognize because they are from MTRIC, where I also analyzed characteristics. And once we analyze the characteristics, we have, for example, the shape parameter of this gamma. Then we can plot all of the shape parameters in a 1D data or in a 1D parameter space. Well, space, it doesn't necessarily have to be plotted. It can also be, well, a 5D parameter space where we plot all of the different parameters. And then the main goal or the ideal goal of my thesis subject will be to plot all of these parameters in parameter spaces and then do some kind of machine learning. So this will either be clustering if we don't have labeled data, or if we do have labeled data, well, we can first train an algorithm and see how well it performs on unseen data. And basically what we are aiming for is, for example, to be able to distinguish between type 1 and type 3 ELMS, or type 1, type 2, type 3, type 4 ELMS. I don't know if you know, but there are different kinds of ELMS. So this would be very useful if we could recognize them. Other applications include reconstruction of plasma 2D profile in this nice paper by Diogo Ferreira, whom I don't know, but he seems to be a very good scientist. And so this can be done right by using a convolutional neural network or a recurrent neural network to predict plasma disruptions. This is also very popular, and the main use of machine learning is disruption prediction, basically very close to what we are doing. So real-time prediction of whether a disruption will happen, and also real-time feedback. So we can teach the machine, okay, something is coming, prepare for it, or even better, do something so we can avoid the disruption. Because as you know, avoiding disruptions or mitigating them will be crucial for further fusion reactors, especially for large scales, one like demo or further. Okay, so usually this part is called take-home messages, but since I assume all of you are already at home, these are stay-home messages. So there's 3 of them. The first one is machine learning is a very broad notion with many different models and algorithms. I tried to give a short, although it's already approaching half an hour, I'm very sorry for this, overview of machine learning. I hope, well, you get to know at least some points. Then 2, you have applications in all domains. As I said, there's lots of different applications, pricing, and so on. But then the 3rd one, and maybe the most important one, of course, fusion applications are on the rise. It's only very recently that machine learning has made its introduction into our field. But I know, for example, now, I think in ASDEX or in Wendelstein, they are looking for a lot of machine learning engineers. So this is something very popular and very rising now that we are gathering a lot of that. So if you're interested by machine learning, make sure to check these different sites or platforms. They are very useful. Google DeepMind, Towards Data Science, Kaggle, Archive, which is where most of the machine learning papers are published, because the world is changing so quickly of machine learning that there's no time to publish them in real journals, because it just takes too long to publish them. So they publish them here in this open source platform very useful if you want to search for some information. So I hope you found this at least partially interesting. You learned maybe a bit. I know it was pretty basic, but I did this, so I hope at least you got some of the concepts. And feel free to contact me about this. I'm not an expert either in machine learning. I just find it very interesting and fascinating. And well, I hope you at least partially do so. Thank you.
So thank you very much, Robin. That was a very enjoyable talk.
Thank you.
For myself, had a lot of fun. And the floor is open for questions. So if you please raise your hand in the participant box, which you can find on the menu bar below. So Alex has the first one. Go ahead.
Yeah, okay. First of all, thank you, Robin. Very nice presentation. This is not a question more about machine learning itself. It's more about how are you tackling such a master thesis? Because as I see, first you had to learn about machine learning and then apply that knowledge to fusion. So
yes.
How are you doing with this kind of double work?
Yes, so basically, well, in the first semester, I followed the machine learning course in Gent, which was a very, very interesting one. I think maybe the most interesting course I had in university. A lot of work, but a lot of work most often means that you also learn a lot. So this was quite useful. So this was what I focused on the first 6 months. Also get to learn Python because, well, we are also gonna publish the algorithm in Python. So I had to learn Python at the same time because I couldn't write Python or I didn't know. So this was a first big task. And then now second semester, we are really diving into the data analysis, also a statistical modeling side of things, trying to find new expressions for distributions that have not been done before. So quite theoretical, quite, yeah, as I said, focused on data analysis. And then we are not yet at the machine learning part. So this is a surprise to come. Then we will know if there's something interesting. It can be very well that after all of the effort we do and we get the parameters piece, we do the clustering and we see there are no clusters at all. So this is possible, of course, but still this is of course research and this still provides useful information for further research to build upon. So yeah, it's quite a big task and we have to divide it in separate subtasks, and then only in the end we will know if it's successful or not. Yeah.
Okay, nice. Thank you. Very, very impressive, I must say. Very impressive.
Vignesh, go ahead. Here you go. Vignesh, did you have a question? Maybe a microphone issue. You can also write it in the chat if you'd like. Okay, then maybe in the meantime, I'll ask a question. Robin, does the shape, when you're doing clustering, is the shape important? How how is it taken into account in an algorithm?
Yes. So
I mean the shape of the clusters, of course.
Yes, yeah, I see. So like this, for example. Now I just used ellipsoids for the clustering. This is most common to use circles or ellipsoids for these clusters. But you have different examples. It also depends on what algorithm you use. Let's say here I used k-means clustering, which is a specific type of algorithm that will focus on the mean of the cluster, and then we'll calculate the distance to the mean. And so in this sense, this will always be a circle or an ellipsoid. So for the most or the easiest algorithms, always use this. But basically, you are free to or you can apply whatever cluster you want, but you will have to go to more complicated algorithms. If you want, you can get like spirals or well, squares is easy because you can just do 2 lines of linear regression and you have your squares. But yeah, essentially the cluster shape is something which goes together with the algorithm. So let's say if you want to use k-means clustering, you will have to deal with ellipsoid clusters. So if you think that ellipsoid-like clusters are not fitted for your problem, you will have to use another algorithm. This is what I was talking about when I was talking about experience. So you have to know what, or at least partially know what you will expect. So if you expect there to be like spiralic clusters, don't use k-means clustering, use some kind of neural network or use another type of algorithm. Yeah.
Or could you make like a multi-layer machine learning to determine what the shape of your clusters should be? Or
well, multi-layer machine learning is basically a neural network, right? This uses a convolutional neural network, uses different layers and then uses this output for the next layer. And then basically it will find the best cluster by itself. You don't have to say what cluster it will be. But as I say, neural networks are quite complicated, but they indeed use this concept of stacking different layers, as you say, and then trying to find out by itself. But unsupervised learning, as I said, you also have to be careful to interpret results, right? Because maybe we can say these are 2 clusters, but maybe this is just one big cluster. We don't really know. So that's why you always have to be careful. But there can be very, very good results, of course. As you see, the recommender systems, most often they work quite well. They suit your favorite music or your favorite video. So yeah, it can be very powerful. Yes.
And since you're on this very nice slide, do you have examples or do you know yourself how to do feature extraction? Because I've programmed some very simple neural networks myself, and I heard about this possibility of extracting knowledge from a network, but I've never been able to sort of grasp how this could actually be done.
So you mean feature extraction from images, or how this is done? Or
yeah, like eventually how does your neural network learn that the ability to determine that the dog has a 13.5 centimeter tail and not a 5 centimeter?
Yeah, I think what well, I'm not an expert in neural networks, more in well, we used more the basic machine learning algorithms, but neural networks, they also look for the optimal features themselves again. So you have to present a lot of images, and it will extract a lot of different features, and eventually it will select the features that are most relevant for the results. But most often these are not length of the tail or diameter of the ears. These are difference in neighboring pixels. What they also use often are wavelet transforms. These are so-called well, you take images, square images or square windows, let's say, sorry, of these images, and then you do wavelet transforms, or you compare this to other areas, and then you extract the features yourself. There's also, if you apply classic machine learning, so no neural networks, because as I said, they learn the features by themselves. If you apply classical neural networks, classical machine learning algorithms, this is also something which is very experience-based. What kind of features do you want to extract? We had a big project last semester where we had to develop an algorithm that was able to classify 11 different types of animals. And so this was one of our main tasks, to try to find out which features are very characterizing for these specific types of animals. And so there's a lot of information out there. You have sieved features, surf features, which are quite complicated. So again, they look at pixels that are very different from neighboring pixels, and stuff like that. So yeah, it can get quite complicated, a lot more complicated than diameter of the ears or length of the tail. Most often the features don't have a tangible feeling anymore. You don't really know what they represent. We just know that these features are able to correctly identify these specific images.
Thanks. I think you have a question in the chat, so if you want to read it out loud and then answer it, or I can read it for you.
So essentially, you are building a classification algorithm for the different kinds of ELMS. I'm guessing the first approach is to identify the features. What algorithm are you using for that? And once you have the features extracted, what classification algorithm? Also, where are you sourcing the data from? So the data that we are working on now is Gent data. I think I'm allowed to say that. But we will also incorporate data from D3D and Compass tokamak, and maybe also ASDEX upgrades. So this is where we get a lot of data from. And indeed, the classification between different kinds of ELMS is one of the goals, but it's also just a goal to establish a nice characterization of just one type of ELM. Let's say a type 1 ELM, we can say, okay, we fit a lot of different distributions. Then we have a lot of parameters, and we can say, okay, this is supposed to be the real parameter. So what we do for now is we just fit the distributions, and then we have these parameter spaces. So the features are essentially, just the shape parameters and the scale parameters of the distributions we fit. So we fit distributions to the waiting times and to the durations of ELMs. So time between ELMs and also the duration of an ELM, because this can be characteristic whether it's type 1 or type 3. And then we fit the distribution, we get the shape parameters. So these are the features. And then once we have the features, the classification algorithm, we are not there yet in this stage, as I said, but this probably won't be any very advanced model like KNN or I'm sorry, it will be KNN, like a CNN or RNN, like some kind of neural network. It will be something like KNN, so K nearest neighbors, or how is it called? Yeah, centroid classifiers. Pretty basic, let's say, algorithms, but they can give a first indication about what kind of clusters we see or what kind of classifications we have, and then we can work further. The problem is we have a lot of unlabeled data. So as I said, we have some labeled data, but also a lot of unlabeled data where we don't know if it's type 1 or type 3. And this is the problem you encounter often. So this is called semi-supervised. You have some labeled data, but a lot of unlabeled data, and then you will have to work further. So as I said, this will work for the couple of months. Yes, basically this is what we're trying to do. So see if we can characterize LM waiting times or LM durations by some kind of distribution, and then well, hopefully it's irrespective of device, so it's scalable, because this is of course the wet dream of each fusion scientist, to find some kind of scaling law for anything. So this is the final goal, and well, I can inform you in about 3 months, more about 4 months, what will be the result. So yeah.
Okay, so I see no more questions for now. I might ask one more myself. I understand that your supervisor was one of the first people who tried to employ machine learning in Fusion. And you mentioned, so your own application to ELM recognition and characterization. Mm-hmm. You also mentioned the more widespread application to disruption prediction and mitigation. Mm-hmm. Do you know of any other applications going on, or ideas that people have had about mm-hmm. how to involve machine learning furthermore in the field of Fusion?
Well, so one of the ones I gave was this 2D reconstruction, which Diogo Ferreira used. So the first point, he used convolutional neural network to reconstruct 2D plasma profile. As you maybe know, this can also be done by tomography, but he tried to use a neural network to reconstruct it. And well, he got some nice results, as you can see here. So this is another application, but as you can see, these are very, very recent papers. Also, this one is from 2018. So I think we're only now starting to see what are the possibilities or what are the options for machine learning inside the fusion world. Let's say the one of predictions, or ELM, is the most investigated one up till now. As you say correctly, like my promoter, so Professor Verdolagen, was one of the first ones to do this. Also, the work I present here, like this work and this work, is mainly based on work he has already done in the past and on previous PhD and master thesis students. So we are just building further on this pile of knowledge, what we already have. So for sure, this is not all my work. A huge part is also carried out by other people. Yeah.
I think there's also a very mediatized work in collaboration between Google and
yes, I read about this. About the startup company in the US, right? Or a fusion company in the US that is involved in. I think I had.
Is that for scenario development, or was it something else?
I'm sorry, what?
That application, was it about scenario development or something else?
I don't know. I couldn't tell you. I read the article like yesterday, actually. Well, I didn't read it. I read through it very. So this is the article which we are talking about. So this is indeed powered by Google AI, and as soon as Google jumps onto something, it becomes very huge. So this is Google that is cooperating with this company, fusion company called AE Technologies, who are experimenting with the state-of-the-art plasma generator they call Norman. I don't know what exactly they are doing, right? They are...
I think it's a reversed field configuration, but I don't know what the machine learning algorithm is trying to do.
Yeah. Well, here I see plasma debugging. So using sparse data from the machine sensor to try to infer the internal state of the plasma. So yeah, I can also see Vicky's typing in chat. So DeepMind has just announced their plan for next year, and fusion is a core part of it. So DeepMind is like the holy grail of for machine learning people. So this is Google's company where they do all of this deep learning, basically, like the AlphaGo Zero, which I gave you an example from, this very nice GIF. And so apparently, I'm not aware of this. Next year they will implement, or fusion will be a core part of it. As I say, it's really on the rising now that the train is starting to run. But I think in the next couple of years it will go full speed, and everyone will jump onto it. So yeah.
So Vicky wrote something in the chat which I'm gonna read for the purpose of people who see the talk afterwards on YouTube.
Yeah.
So DeepMind has just announced their plan for the next year, and fusion is a core part of it. They created an optimetrist algorithm for tri-alpha energy, TAE, which scans the parameter space and finds the optimum condition to generate maximum heat output. All right. Optometrist. All right.
Yeah. So basically trying to find the right conditions for maximizing the efficiency of the reactor. So this is also something that can be done, right? Just generate or just gather enough data from all of the discharges and then do. This may be also one of the problems why for now it's maybe a bit difficult to apply deep learning, so convolutional neural networks, because for neural networks you really need thousands of data. And well, over time there has been already a lot of discharges, but we will need a lot more to be able to extract the most out of the data we get, right? Because it's not so easy to get discharge data as it is to get an image of a cat on the web. So
yeah. So are there any more questions? Feel free to raise your hand now or leave it down until the next talk in 2 weeks.